Hello, everybody. Um, Thanks for listening. Thanks for your interest on this technology. I'm gonna describe some background information about the technology we invented here at Oak Ridge National Lab. We call it direct contact ultrasonic drawing technology. My name is Ayub Momen. I'm the principal investigator of this project, and we are working in Energy and Transportation Science Division at Oak Ridge National Lab. So let's start from some background. Energy usage of the drawing technologies in US, if we want to categorize it into residential and commercial buildings, which general these buildings consume somewhere about 40% of US energy. 2% of that energy goes to the closed drawing, and that's a huge number. On the industrial sector, also there are a lot of industrial processes that uses drawing technologies, like food drawing or chemical drawing or so many other drawing processes. And in summary, almost 2% of the energy use in that sector also goes to the drawing. So if we add up these two numbers, the drawing technologies in the United States actually consume 1.4 quads of energy, or equivalent to somewhere about $14 billion of utility bill or energy bills annually, and that's a huge number. This technology has potential to significantly reduce those numbers as it commercialized and be applied in different fields. Specifically on the closed dryers, mainly because our project was focused on the closed drawing applications, but the IP that we developed can be applied on different drawing technologies. Let's focus on the closed drawing in the residential buildings. Almost 85% of American homes have closed dryers, and that accounts for 6% of the utility bills in residential buildings, and that's a large number. Somewhere about $9 billion energy bills goes just to the laundry or just to the closed dryers, and that's a huge number. It's expected that the average sale of closed dryers in the United States keep growing with the rate of 1.8% in the next few years. The conventional closed dryers work based on the evaporation of water, or based on heating. What they do is that they take electricity from the wall outlet. They have a resistive heating element. As air passes across that resistive heating element, it heats up, and the hot air passes across wet fabric and evaporate water, and that's how they achieve drying. But the latent heat of evaporation of water is so huge. It's somewhere about 2400 kilojoule per kilogram of water removal. So the process overall is very inefficient, and considering all the inefficiencies in the conventional dryers, actually they are operating at their at 55 to 66% of their theoretical efficiency limit. So there is not much room for improvement in the existing improvement of the efficiency in the existing dryers. Conventional dryers have energy factors of about 3.5 pound of dry bone fabric per kilowatt hour of energy you are putting, and they have drying time of about 40 to 60 minutes. Some newer technologies that are based on the heat pump, let's say heat pump dryer technologies, they achieve a slightly higher energy factor of about 5.5, but the drying time is slightly longer. It's about 60 to 120 minutes. So what we developed here, or what we proposed, was that conventional dryer use heat to evaporate water, and the latent heat of evaporation of water is so huge. So instead of doing that, we propose to use high frequency vibration to shake fabric at high frequency. And when you are shaking fabric at such a high frequency, actually moisture comes out of the fabric in the form of cold mist. So we are not evaporating water, we are just mechanically extracting the moisture from the fabric. How we achieve high frequency vibration is using piezoelectric transducers. Also, some people call them ultrasonic transducers, and that's how we generate high frequency vibration. Let's go a little bit dive into the details. Let's say if we have oscillating um, oscillating system that have oscillation like a sine omega t, where omega is the frequency of the oscillation. The driving force that tries to take the moisture out of the fabric is proportional to the mass of the droplets inside of the pores of the fabric times the acceleration that is induced by piezoelectric transducers. What is resisting against moisture removal is actually capillary force that's proportional to the surface tension times diameter of times the diameter of the pores. If we want to show it in a graphical form, if we do the analysis, some basic analysis, as you can see in the figure on the right, for different pore size, the x-axis is average pore size in the fabric in micrometer, and the y-axis is final remaining moisture content in the fabric. So at low frequency, like the green line, for very small pores, actually we cannot remove the moisture from the fabric, mainly because the surface tension or the capillary force is large, and we cannot remove the water from the fabric. But if the pore size become larger, definitely you can remove some moisture and reach to moderate drying, as you can see in this graph. In order to activate the smaller pores, what you have to do is that to increase the frequency, as you can see here. As soon as you increase the frequency, you are increasing the driving force. Definitely you can reach, you can activate most of the pores inside of the fabric and reach to even lower final remaining moisture content. The same goes on and on. As you increase the frequency, you can achieve better and better drying, but you have to pay for it. Here on the left graph, you see that as you increase the frequency, the energy consumption of the piezoelectric transducers, or the energy consumption of moisture removal, is going up. So there is a sweet spot at which we can achieve both good drying and good efficiency at the same time, and that's what exactly we did in this project. If you see these numbers, you can see that there are huge potential for improvement of the efficiency if we can design the system appropriately. So what we have developed in the first year of the project, actually we focused on 4 main areas, research areas. One was identifying and evaluating the correct piezoelectric transducers for these drawing applications, and we down selected actually two specific transducers among 150 transducers that we studied. We identified and evaluated the correct power signal. We realized that the amplifier has a big role on the efficiency, on the final efficiency of the system. So we actually customized the design of the amplifier and come up with one of the best designs. We also work on modulating or designing a modulating transducers so that we can modulate or scale up the system easier later on. And also we worked on developing the mist collection mechanism. So at the end of the year one, this was a prototype that we had, which could dry 14 square inch of the fabric. As you can see, the moisture could easily be removed from that wet fabric sitting on the piezoelectric transducers. So the goal of the year one the goal of the project at the end of the year one was to dry at least 4 square inch of the fabric in less than 20 minutes. What we achieved is that we could actually dry 14 square inch of fabric in 7.5 minutes. Also, we could modulate the system. So the systems that you can see here consist of 24 transducers. We also did a study on the effect of the number of the fabric layers. As you can see here, we showed that as you put several layers of the fabric on top of these systems or piezoelectric transducers, the drying time linearly increases as you put more and more number of the layers. So after that point, actually something nice happened to the project. We developed a first order model for the system, and our model inspired a game-changing insight. So what we modeled when we modeled the system, the piezoelectric transducers and the fabric on top of it, we realized that at low frequency, what will happen is that piezoelectric transducers and the fabric are mechanically coupled, so they are going up and down with each other. But as you increase the frequency, as you can see here in the red line, is the high frequency vibration of the surface of the piezoelectric transducer. What will happen is that the piezo is gonna kick the fabric, and the fabric is gonna go up, and it's gonna take long time for the fabric to come back on the surface of the piezo by gravitational force. So during that time, which is in microsecond, we realize that we don't need to power the piezoelectric transducers. So it's not necessary because they are not coupled together. So what we come up with from this analysis was that why not driving these piezoelectric transducers at much lower duty cycle and save a lot of energy. We did that actually. In order to do that, we had to design our custom amplifier, and by doing it, we could actually double the efficiency of the drawing and could achieve the drawing performance as low as 712 kilojoule per kilogram of water that we removed. Putting it in the perspective, this is somewhere about 5 times more efficient than if you wanted to evaporate water. Another question was that this technology generates a lot of mist, mechanically extract the water in the form of cold mist. What can be done with that cold mist? So in a part of this research, we focus on how we can design a mist collection mechanism, and we realized that by putting few layers of typical lint filter and passing the mist across that, we can collect the water, and water actually can be drained easily. That's one way. Or if there is any venting system available, you can just simply vent it out. So in either case, the final design of the closed dryer can be either vented dryer, or the water can be collected inside of the dryer machine itself. So there are a lot of flexibilities in this area as well. So few months ago, actually by the end of year 2 of the project, actually we scaled up our system to a prototype, a modular prototype that you can see here. This is a close-up picture. There are a lot of piezoelectric transducers placed on the PCB boards, and this is another picture from the bottom of that PCB boards, and this is the prototype, the latest prototype in action, and I'm gonna run the video for you. So what you are seeing here is that we put a wet fabric on top of the piezoelectric modules we had. You could close the lid or not, it doesn't matter. And as we were increasing the voltage or amplitude of the vibration, you can see a lot of cold mist is coming out of that wet fabric. The interesting thing in this technology is that this cold mist is not warm at all. It is just as cold as room temperature, and that's why we could reach to such a high drawing efficiency. So this process goes on and on for somewhere about 4 or 5 minutes, and we could reach to the complete drawing in 4 or 5 minutes. So the prototype that you saw has ability to draw a small size closing in few minutes at much higher efficiency. As a matter of fact, we put a small pan, actually that is the pan from my 2-year-old son, and we could actually dry small pieces of fabric, so small pieces of clothing. So this is the largest prototype we have so far, but we are working on scaling it up. So let's look at the results, some efficiency results of this prototype. So the x-axis here is the remaining moisture content of different configurations. Always we start with 57% initial moisture content, mainly because when the clothing comes out of the washing machine, usually it has 57% moisture content, and we dry it down to, most of the cases, down to 20% remaining moisture content. What we realized is that below 20%, the efficiency of the drying is through this method is not very good. So probably this technology is working the best for moisture content above 20% and even above 57%. So it can dry anything from high moisture content down to 20% very efficiently. So the y-axis here is joules per gram of water removal that we put on the piezoelectric transducers, and we put two lines. One line is energy needed to evaporate water, 2400 kilojoule per kilogram of water removal, and also another green line here is typical resistive heating based conventional dryer efficiency range. So anything below these two numbers are better than evaporating dryer and shows a better performance than the conventional system. And as you can see, in most of the cases and most of the cases that we configuration that we run, the efficiency is or the energy consumption is significantly lower than evaporating drying. Means that the efficiency of the drying is much better than the conventional evaporation based drying. This slide shows the drying time versus remaining moisture content for the same test. For most of the cases, actually the drying time or the drying time versus remaining moisture content was following almost a straight line. In some cases it was faster. In some cases, it was slower. And this table actually summarizes the results we got. So the best results we got so far shows that the efficiency of our drawing could be as high as 16 or even 18 pound per kilowatt hour of energy input to the system. And to put it in a perspective, the conventional dryers have energy factor of about 3.5, and this is a significant improvement over the conventional dryers. Definitely, we don't have a full-scale system, so there are a lot of other components needs to be added to the scale up system. But definitely, this shows a promising result so far, and showing that we can actually dry much more efficient than evaporating water. So at this point, we are actually at the end of the year 2 of the project. When we started the project, actually the first prototype we had, we could dry 1 square inch of the fabric, but at this point we can dry somewhere about 300 or 400 square inch of fabric with our prototype. And from efficiency point of view, we started with energy factor of somewhere about 3 or 4, and at this point of time our energy factors are beyond 12 or 15, as you saw in the previous table. So we significantly improved both the efficiency and the scale of the system so far in the last 2 years. And the next step would be we further scale up the system, and probably we are going to retrofit the full-scale dryer drum with the piezoelectric transducers, and also design some alternative systems for the full-scale dryer other than the conventional full-scale drum dryer. And also we have to show that we are going to achieve the energy factor more than 10 and drying time of less than 20 minutes in the scale of the system, and that's our target. So some frequently asked questions. We have demonstrated this technology to many groups, and they come back with so many questions, and I summarized few of those questions here, and I am trying to answer them as short as briefly as possible. One of the questions is that what happens with the mist after it produced. So as I described in this presentation, it will be either vented out of the building or can be collected with the mist collection mechanism that we designed under this project. Another question is, who is the owner of the IP on this technology? The answer is that ORNL is the owner of the IP, and actually the IP is only belongs to Oak Ridge National Lab and not the other entities. Can the technology dry material other than the fabric? The answer is that it depends. We would like you to contact us if you have any specific applications, and we can help you to figure out whether this technology can be applied to your system or not. But in summary, what we have done so far, our main focus was on fabric drying. And we showed the technology showed a great potential in that area. We also put a little bit of time and showed that the technology can be applied on for paper drying and also cellulose drying. We have done few testing on small rubber pellet pieces. That was not successful. So what I'm saying is that it depends on the application. So we would like you to contact us, and figure out whether it is applicable or not. Another question is that how much drying efficiency improvement has been achieved over the conventional dryers? The answer is that the best results we have got so far shows 3 to 5 times improvement over the conventional dryers depending on the configuration. How far it can dry? The answer was in one of my slides. This technology has shown a great potential to dry fabric down to 20% remaining moisture content. Below that level, it is not efficient, but technology is very efficient at much higher moisture content, down to 20%. What will be the final form factor of your dryer? Again, it depends on the final application, whether we are talking about clothes dryers, small clothes dryer, large clothes dryers, or industrial application. So the design is very flexible, and we can work with you to design the system appropriate for your application. The impact of ultrasonic dryer and the quality of the fabric. So we have not done any study in this field yet, but we are expecting that the quality of the fabric and the drying to be better than the conventional system, mainly because we are not heating the fabric to high temperature. So that reduces the stress, the thermal stress on the fabric, and hopefully that's gonna help to reduce the stress on the fabric, and you probably reduce the lint generation during the drying period. But again, that needs to be tested definitely. How soon will the technology be available in the market? The answer is that it depends on the field of use. For the clothes dryer application specifically, we are expecting that the first product to be in the market in somewhere about 3 to 5 years from now. Can this technology be combined with a washing machine so we can have a single washer and dryer unit? The answer is that it is possible. Definitely there are going to be a lot of challenges there as well, but that might be one forms of the final design. But we haven't actually done that yet. Have you tried drawing multiple layers of the fabric or different type of the fabric? So the answer is that on this small scale system, we dried multiple layers of the fabric, up to 9 layers, as you saw in my presentation, and also we work on probably four different standard fabric different type of the fabrics, and yes, the technology works for different types of the fabric. What we haven't done so far is to dry much thicker fabric like jeans, and that's one thing that we are gonna study in the next phase of the project. Thank you so much for listening to this presentation. If you have any questions, you can always email me. My email address was listed in the first page of the presentation, and we would do our best to answer your questions as the best of our knowledge. Thank you so much.